Hi guys, the lesson that most people are working on today is about composing functions or composition of functions. This is another function operation like we saw in the last lesson where we were adding, multiplying, subtracting, and dividing the functions. Now what we're going to do is use the output from one function as the input for a second function. And we call this composition of functions. It's notated with this, it has this small circle here in the middle, and I want to make sure that this means f composed with g of x, and here we read this f of g of x. The domain of the composition is all of the values of x in the domain of g such that g of x is in the domain of f. And we'll look into that in a little more detail. So here we have three sets of values, right? This is a nice table that we've got here. And it shows us that we start off with these values of 1, 3, and 5, right? And then this function g takes 1 and it maps it to 4. And when we plug in 3, it maps to 6. And when we plug in 5, it maps to 8. Now we have a second function where where 4 maps to 8, 6 maps to 12, 8 maps to 16. And then if we want to, we can think about the composition of these functions where, see, these are the inputs, right? This is the input for g, and then this column would be the output. It is also the input column for f, and here would be f's outputs. We also have this, though, where if we have f composed with g, or f of g, the input of g becomes it gets the outputs of f. So to find f of g of 1, first we want to find out where does g of 1 map to? Well, g of 1 says the output is equal to 4, right? We see that here. Then we use 4 as the input to f. So we always start, if we notice, on the inside. See, this letter is closest to 1. So first we found g of 1. Then we go for the outer function, f, and use the input that we got from the first. So f of 4, well, if we look here, 4 maps to 8, so f of 4 equals 8. So f of g of 1 is equal to 8. The order of operations is the same as the order of operations for numbers and expressions. So to find f of g of 3, first, let's go ahead and try this one. Let's see if we can evaluate f of g of 3. Oh, and excuse me, I do have one extra parentheses in here. Let me remove that. F of g of 3. So let's look at the inside value first. What is g of 3? Well, g of 3 is 6, right? When we input 3, we get 6 out. So we want to now, g of 3 equaled 6. So now we want to plug in this value, right? G of 3 was 6, so let's plug that into f. What is f of 6? Well, here is 6, and it maps to 12. So then we can say that f of g of 3 is equal to 12. And as I've been saying, the composition, right, this function here, also this notation is read f of g of x. Right, f of g of x. So it's whatever's on the outside is the letter we'd say first. We could have two functions, h of x and m of x. And if I were to write this expression, I would say it h of m of x. Be careful, let's not confuse some notation. So in the last lesson, we were doing multiplications of these functions with the function operations, and we had f times g of x. That is not the same thing. That was where we took two functions and multiplied them together. Now we are actually inputting one function into the other. Let's look at evaluating composite functions. So here I've got a couple of different equations. F of x equals 2 raised to the exponent x. This is that function that models life, right? Powers of 2. G of x is 7 minus x. And we want to find the value f of g of 4. So step 1, let's find g of 4, right? We've got to find that. That's important. So I'm going to plug in 4 into the equation for g, right? So we had 7 minus x, so I have 7 minus 4, and I get 3 is my output there. Now I want to take this output value and plug it in now for f, right? Because I found g of 4, it's 3. And then this now becomes f of 3, right? That's what happens when we go from this step to this, is we found this number, it was 3, let's replace that g of 4 with 3. Now we need to plug in 3 to this equation, right? 2 to the x. Well, if we plug that in, f of 3, 2 to the third power is the same thing as 2 times 2 times 2. Recall that that does not mean 2 times 3, it means 2 times itself 3 times. And we get 8 as our final value. So f of g of 4 is equal to 8. Let's look here. Now we're looking at, we want to find g of f of 4. So recall in our last example, we were looking at the opposite case, and we'll see here that we're going to end up getting some kind of different values, right? But you notice now this is f of g of 4 is what we just did. Now we're looking at g of f of 4. So again, step 1 is find what is the value, the function value for that inside, right? Let's find f of 4 so we can plug that into where we have this in our equation. Well, we know that f is 2 to the x, so we plug in 4. Recalling again, that's not 2 times 4, it's 2 times 2 times 2 times 2. And 2 to the 4th power equals 16. Now we can replace f of 4 into that composition notation and we now want to find out, well, what happens when we plug in 16 to g? G was 7 minus x, so 7 minus 16, we end up getting negative 9 as our value. So g of f of 4 is equal to negative 9. Okay, here let's look at one more example. Now we have a couple of different functions. We have f of x is equal to 2x minus 3. And x squared is equal, or excuse me, g of x is equal to x squared. And we want to find these values, f of g of 3. Well, again, we have to remember the first step is find g of 3. So we can replace g of 3 in the composition notation with the value we want to plug into f. So if I take 3 and I plug it into my equation for g of x, I get 3 squared. Again, remembering that's not 3 times 2, that's 3 times itself twice, right? So 3 times 3. And we end up getting 9. Now again, remember, we're going to take this value that we got for g of 3 and plug it back in right in here for this function. Instead of having g of 3, we'll put in 9. Now we want to know what happens when we plug in 9 to f. Well, f is 2x minus 3. So 2 times 9, that would give me 18. And I'm subtracting from that 3. So I get a final answer of 15. F of g of 3 is equal to 15. Now let's go ahead and see if we can try it backwards, right? We tried f of g of 3 last time. Now we're going to find g of f of 3. So instead of finding g of 3 first, now since f of 3 is on the inside, we need to find that first, right? That's going to be our first step. Well, f of x was 2x minus 3, so plugging in 3, we have 2 times 3, which equals 6. And we subtract 3 from that and get 3. Now remember, we're going to take that output value for f of 3 and plug it into our composition notation. and figure out what is g of 3. What do we get when we plug in 3 for x in our equation for g of x? Well, it was x squared, so 3 squared, recalling that equals 3 times 3, and we get 9 as our final solution. G of f of 3 is equal to 9. You can also use algebraic expressions as well as numbers as inputs into functions. This is what we call finding a rule for f of g of x. We're going to substitute the rule for g into f. And when we say rule, it's just really that little equation, right? If I have f of x equals x minus 1, this little piece here on the side, that is the rule. Right? I want to put that rule in for x in another equation. So let's look at what that looks like. Okay, so you can have different functions, and I will say this one's a little more difficult than some of the things that we're doing online, but I think it really it gives us a good idea of what we would be doing here. So it says, given that f of x is x squared minus 1 and g of x is x over 1 minus x, we want to write a composite function or a rule for f of g of x. So what that's telling me is that everywhere in f that I have an x, right? I only have one here, x squared. I need to plug in, instead of a number, I need to plug in this other entire equation into it. So if you notice here, f of g of x is really f of this other function, x over 1 minus x. Now let's look here. So we had x squared minus 1. And if you notice now, this x squared has had the substitution of this other equation in it, x over 1 minus x squared minus 1. Now this is a lot of algebraic simplification that happened here, which is kind of beyond where we're at right at this moment. So we're just going to leave this solution here, but it gives us an idea of how we start, right? That this is something that we just want to make sure that it's the idea of plugging one equation into another equation. Now, one thing we've got to be really careful about, and we've seen this a little bit so far, is they've talked to us about the domain of these, right? What x values can we possibly plug in and get a number out of it? Well, we need to remember that in math, we can never, this right here, we can never have. We cannot divide 1 by 0. This actually, if you put it into your calculator, and let me show you here, if I take a 1 and I divide it by 0, I get divide by 0 error. And on some calculators, let me show you my TI here. On this calculator, if I take 1 and I divide by 0, it just, again, it says divide by 0 error, because you cannot divide by 0. It's like trying to give something away to no one. So we need to think about these expressions as what is going to make the bottom of this fraction 0? Well, here, what could I subtract from 1 to make this value 0? Well, that would be the value 1. So here it tells me the domain of this is that x cannot equal 1, right? This can't be 1, because if it is, the whole bottom of that function becomes undefined, right? And that's what it says. G of 1 is undefined. That's another term for this, is we call it undefined, meaning it has no real number solution. I'm going to skip this page, and I want to go on to the next example. Here I've got two more functions, f of x, where we have f of x is 3x minus 4, and g of x is the square root of x plus 2. And they would like us to write the composite function for each, and then to state the domain. So first we want to take the function g of x, right? Whatever is inside of the composition notation, which is this equation here, and we need to plug it in where there's an x in the other equation. So if you notice, now we've got 3, and instead of x, we've written this entire equation, the square root of x plus 2. And then we still bring in our negative 4, right? Because that's the rest of our equation. Now we've got to be careful, right? We've got to distribute that 3 to both of those numbers that are inside the parentheses. And that's why we end up getting this 3x plus 6 minus 4. Now let's be careful. We've got to do a little bit of simplification, right? 6 minus 4, that yields us 2. So this is my final solution. If I have f of g of x, and there's a rule I need for it, now I can simply plug any value in here. But I'm wondering, well, is there any number that I can't put into a square root? Well, if we recall, it turns out we can't have square roots with a negative underneath it. This is also, it's undefined for what we call real numbers, right? All of the counting numbers, or for, it's undefined for negatives. So we can put any value in there as long as it's greater than or equal to 0. Any square root function, we can find the square root of 0 is equal to 1. But as we'll find out later, if we put a negative value in there, the square root of negative 1 actually equals a special variable called I, which is what we call an imaginary number. So for this function here, anytime you have a square root, it always has to be a number bigger than or equal to 0 that we plug in. Now let's look the opposite way. Here we need to know, and I'm not going to go through the domain of this one because it's more complex and we really haven't gotten into the solutions for what we call radical functions, which are these square root functions. But I do want to look at what it looks like when we simplify something like this. And actually, if you notice now, so here we're taking f of x, right? That's what's inside. It's always inside that we're plugging in, that we put in for x, right? So I need to take this entire function and put it underneath that square root. So here they've done that. Well, I cannot split this up. That minus sign with the 4 in there really kind of sticks 3x and minus 4 together. So this is actually would be our final simplified solution. Quite frequently when we're looking at square roots and we're doing this plugging in another function into them, there's not a lot of simplification that we can do. And I think with that will be enough examples for now. If there's any more stuff you guys are working on and you're stuck, please let me know and have a great day.